Okay, good afternoon, folks. I'm going to have a few comments about the homework assignment that is due right now. And I feel like I have to extend the deadline until this coming actually Thursday because there have been some misunderstandings. One correction. On the 24th of February, when I was covering this buck-boost converter and how to actually develop the small signal model, what I missed was this little connection over here. This thing should be shorted, okay? So if it is not shorted, your circuit is not going to work, and you are not going to get the right transfer function. So because of this thing that I forgot on I think last week on Tuesday or Thursday, I'm going to extend the deadline until this coming Thursday. Also, I was looking at some of the solutions that you have submitted, and this is not what I had asked you to do. What I have been asking you to do is identify the single pole double throw switch in your system and replace it with the network that I have on the right hand side of the screen. I do not want you to start with the original equations. I do not want you to look at Erickson's book and follow those equations. I want you to identify the single pole double throw switch and replace it with the network on the right hand side of the screen, and the rest is basically circuits 1. You have to find a particular transfer function in your circuit. Question?
Can you please say this after 10 minutes when all the people have come, please?
I can't wait. The class is officially starting now, and then I can't really wait. So I'm going to give you guys an example of what I exactly mean by, replacing this thing. Let's say we are trying to analyze the boost converter. So what you see in the boost converter is you have an inductor here. This is the input voltage. Is the reason that the students are delayed? What is the reason?
I think they are still trying to do the homework.
Oh, okay. Well, that they should be punished. You shouldn't put it the last minute. All right. For instance, let's say you are looking at the boost converter. You identify the single pole double throw switch. The only thing is, the command that is applied to the top switch turns out to be D prime, not D, okay? So when you take this single pole double throw switch out and replace it with this small signal model, now remember, whatever was the label of the command applied to the top switch appears in our model. Like here it's D prime. So this is going to be D prime perturbed, D prime perturbed, DC value of D prime, and again D prime perturbed. That's the only thing that you have to do. So this is where you should start for your homework assignment. Again, some of you are actually walking in. If you are not following the procedure that I'm about to present, you have until Thursday before the class starts to resubmit your homework assignment. Okay, so we have identified the single pole double throw switch. We replaced it with the small signal model. So this is an example for the boost, by the way. As I said, the rest is circuits 1. How is it that you can analyze this network? Trying to find the desired transfer function. You can do node voltage analysis. You can do mesh current analysis. Or can you do any kind of crazy stuff that you have learned in circuits 1? As long as it works, that's fine. So for instance, let's say we are looking for GVG. Okay? Which is the audio susceptibility. So remember, it is defined as in these models, we are not really perturbing the load, so we don't have to worry about perturbing the load. But if the duty cycle is not perturbed, how is it that the perturbations in the input voltage appear in the output voltage, basically? So that is all about the audio susceptibility. So the suggestion is replace anywhere that you have D or D prime, replace them with 0. So remember, D prime perturbed is the opposite of D perturbed. And if D is not perturbed or the perturbations are 0, therefore D prime is not perturbed either. So anywhere that I have D or D prime, I should just replace them with 0. So I'm going to redraw this circuit. So this is a dependent current source on D prime perturbations. It's 0, it's open circuit. Excuse me. This dependent voltage source is also 0 or shorted because D prime appears in the description of the source. Excuse me. All right. So all I have to do is, again, going back to my circuits 1 knowledge, try to analyze this network and find the transfer function that relates the perturbations in the input voltage to the output voltage, basically. All right, so it's up to you. Node voltage analysis, mesh current analysis. What I have done is I have labeled this current to be IX. I have labeled this current to be IY. And on the secondary side, depends on what you define. Okay, let's say on the primary side of the transformer, V out perturb appears, so it reflects to the secondary side as D prime times V out perturb. Okay, so also IX could be written as assuming that we know what the output voltage is in terms of perturbations, just divided by that impedance, that is the current that is being drawn in that direction, which is labeled as IX, which is, for instance, the primary side current. Therefore, the secondary side current would be the same thing divided by the turns ratio of D prime, which, if you rewrite it, it is going to look like this. Okay, something like this. All right. At the same time, I can describe IY in another form, which is, this is the current that is passing through this inductor. So I look at the voltage drop, or the voltage that applied to the inductor, and divided by the impedance of the inductor. So on the other side, I have IY is the voltage on the right-hand side of the inductor, which is the input voltage perturbed, minus the left-hand side, which is the reflection of the output voltage, divided by the impedance, which is LS. All right. So that's it. You just make sure that these two equations hold at the same time. And once you simplify this, you will get so this is the transfer function that we are looking for. However, it is not in the canonical form, so you just have to rearrange things in a canonical form. So let me write the canonical form and then make a comparison. All right. So on the left, I have the transfer function that I have. On the right, I have the canonical form. Just make a comparison. And you can tabulate things, but anyway, it is going to look like this. Omega naught is d prime over the square root of LC. Q is going to be okay, I'm kind of showing the abstract version. Obviously, I'm asking you, expecting you to show a complete work. So this was an example. If you are interested in the audio, finding the audio susceptibility transfer function of the boost converter. So as I said earlier, as we started, this is the only procedure that I'm going to accept from you. Do not follow the procedure that comes in Erickson's book, or do not start with the original equations of the boost or the buck boost or whatever converter it is, and do not perturb them. So the whole objective is identify a single pole double throw switch in your power converter and then replace it with this network. And yes, there's a connection here. Okay. And that's it. From that point on, it's just a circuit one kind of a problem. So for those of you who walked in late, I made a correction on the lecture that I had on the 24th. There is a connection here. All right, highlighted in here. Yes?
So when we actually go to find GVD, we should, the V in hat is going to be 0 then?
Right, that's right.
And so that will just be shorted out there.
Exactly. If it is a source of voltage, then it is shorted.
And also it says I load is 0, I load hat is 0.
I load is 0. As I said, we don't really disturb the load, so don't worry about even variations of the load.
So it remains constant at whatever the output current it is.
Yeah, so the whole thing that I load is constant means this resistance is a constant resistance. So don't worry about that. Yes?
The ratio supposed to be 1 to D to D dash in the buck boost.
In the buck boost, the ratio is supposed to be for what transfer function? I think I tabulated them at some point. Let me see if I can find it. I don't remember where they are.
No.
Is it after this?
The question is that whether the ratio of the transformer.
Oh, the ratio of the transformer. Is that the question?
Yes.
For the buck boost?
Yes.
It's D. I mean, depends on what you define as a buck boost, okay? I'm going to draw a different buck boost, and in order to... okay, I don't want to confuse you guys, but okay, let's go with the very classic one. All right, there's an inductor here, by the way. Okay, if you consider this as your buck boost converter, D is determined by the top switch, so it's D. If you consider this as your buck boost converter, okay, then D is here, therefore you should consider D prime. So you only consider that the command that is applied to the top switch, okay? So it depends on which one of these guys you consider as your buck boost. If you do the left-hand side, D is the top one, basically. Otherwise, it's D prime. Question?
So for the tabulation, you just want omega naught, Q, and G naught?
Yes, in it, like in a line.
Just
like
those three, or do you?
Yeah, and yeah, that's it. Actually, yeah, I need G sub G0, G sub V0, D0, those kind of things. Yeah. Any other questions? So as I said, if you have, yes.
So for the buck boost small signal model,
Okay.
the Vin plus Vo, I'm assuming that's a constant. Even if I'm trying to find the control to output transfer function.
The control to output transfer function. Okay, let me look at the schematic over here. Let me bring it over here.
So we node analysis. Nodal analysis.
So for the for the buck boost, you should start with this circuit. So the question is, Vin plus Vout is constant. If you are trying to perturb the duty cycle, is that the question?
Yes.
Okay. So if you are trying to, for instance, find, let's say, G sub Vd, okay? And that is, Vin is not perturbed anymore, right?
Correct.
So that means this is shorted. And that's it. The rest are there. Only thing is Vn is not perturbed. Therefore, Vn hat is 0 basically, or shorted.
To get a canonical form, do I have to substitute the duty cycle or D over 1 minus D for Vn?
For what could be substitute? What the output voltage?
Well,
you said?
to get it to canonical form, Vn is not part of any of those equations.
Oh, okay. If you do that in the end, it's okay. If you have D prime or D, you can substitute D with 1 minus D, or if you can substitute D prime with 1 minus D, or vice versa to make it closer to the canonical form. That's right. You can do that.
Okay. Thank you.
Okay. We had one more question. Okay. Yes.
I just forgot it.
Okay, so it looks a little bit silly. You have to work on it. This is kind of an exercise when you were like 18 or 19 or 35. First time you took circuits 1. I was 18. Actually, I was older than that. I was 19. Anyway, this is just to refresh your memory. Go back to your circuits 1 and see how rusty you are. You have to go and practice and basically solve this, okay? It's not that hard. Okay. All right, so let's get back to our lecture now. So what we did last time was we kind of tried to form a control loop, okay? So we have a converter. For instance, usually our objective is to regulate the output voltage of this converter. By regulation, what I mean is if the input voltage changes, we don't see those changes in the output voltage. If the load resistance changes, we don't see those changes in the output voltage. So if you want to regulate something, for instance, you want to regulate the temperature of this room, no matter how many people walk in and out, or if you open up a window or something like that. So first thing that you do is you have to measure the signal that you are trying to regulate. So if you have a sensor, then you have to compare your measured signal with some sort of a reference. For instance, the room temperature should be 72. This is the number that you have already set. That's your reference, basically. Then the difference between the actual temperature and the set temperature is the error. Like here, the difference between actual output voltage and the reference for the output voltage is the error. And then you apply that error to a voltage compensation network, and we are going to see today what that is. We call it G sub C. And then it's pretty much like a low-pass filter. Think of it as like an integration block, the simplest way of thinking about it. And then if the output of this compensation is high, that means your duty cycle should be high. If it is low, that means your duty cycle should be low. So the level has to be converted to pulse width. So you do a PWM, pulse width modulator basically, and then you have a gate driver because usually your PWM block is not powerful enough to turn your transistor on and off. You need to have a gate driver, which is just a power amplifier. It doesn't really appear in our control parameters. So this is a very typical, feedback loop, control of the, for instance, the DC-DC converter. It's called a voltage mode control. Later on, we are going to see there is another scheme which is called current mode control. So I'm going to start here and write an equivalent model, control model. So we are still discussing the feedback control. So I think we looked at this kind of a control block diagram of our DC to DC converter. We have two uncontrolled or disturbance kind of inputs, which is the variations in the input voltage, variations in the output current or output resistance. They all have an impact on the output voltage. And now I am kind of sensing this output voltage. So my sensor may have its own transfer function. It's usually just a step down, kind of a, gain, scaling down, but sometimes it could be a transfer function. We don't really perturb the reference, but for the sake of, being comprehensive, I'm assuming that it is there, but usually it is 0 basically. So we get perturbations in the error. Then we have a compensation network. We get perturbations in the control signal or VC. And then our modulation block also has a transfer function associated with it. And the gate driver is not coming into the picture because it's just a power amplifier. It doesn't have a transfer function, basically. All right. So from a control perspective, this is what we are doing. Our objective is to find a proper transfer function for G sub C, which is the compensation network. So in the end, we would like to see what would be a good transfer function over here to help us achieve our goals in terms of regulating the output voltage versus against the changes in the input voltage or against the changes in the load current. All right, so what I'm going to do is, again, going back to a classic control class, I'm going to look at this loop gain. Let me use green, for instance. All right. And I call it T, okay? What is important in looking at the loop gain is there is always a negative sign appearing in our loop gain, and we always neglect that. That negative sign comes from here. But when you are forming your loop gain, you always neglect this negative sign. The whole thing is you already know there's a negative sign over there, and forget about it. Don't consider it when you're writing your loop gain. So all I have to do is, identify the elements that appear in my loop and just multiply their transfer functions. So I have a sensing network. I neglect that negative 1. Then I have a compensation network. Then I have a modulating block. And then we have the control to output transfer function of the converter as well. So all of these appear in our loop gain basically. All right. So if I write an open loop equation, I can write the we already had this before. I can write the output voltage as a function of variations in the duty cycle plus, again, this is a superposition kind of a thing, variations in the input voltage minus variations in the output current. The minus sign comes from the fact that the current is flowing out of the converter. All right. So this is a very general equation relating the inputs and outputs of my power converter. However, now because we have closed the loop, I can describe the duty cycle in this form. The duty cycle now that is being applied, I'm looking at here basically, the duty cycle that is applied to the converter is actually kind of related to the output voltage of the converter. So I just have to write that relationship. Negative H of S, G sub C of S, modulation block gain times the output voltage. All right. Plus, in case there is perturbations in the reference, okay? So it's like we're also considering in the very general case that the reference could also be, changing a little bit. All right, so I'm just going to combine these two equations with each other. Wherever I have D, I'm going to replace in the top equation, wherever I have D as the perturbations in duty cycle, I will replace it with the bottom equation. So once you do so, you will end up with this expression. Hold on. 1 plus H times this is GM. GVD GM. Okay. So since we closed the loop, duty cycle is not an independent parameter anymore. It's like an internal parameter. All we did was we just eliminated that internal parameter. All right. So based on what I define as the loop gain, which is H times GC times GM times GVD, you can see that it is appearing here, here, here as our loop gain. So I can rewrite this equation in this form. Remember, all of these things are transfer functions. I just don't write those S thing anymore because it's going to get really large. But like GVG is a transfer function of its own. Okay. All right. So we are trying to actually, write these equations to in the end to find out what kind of characteristics or features we expect from our loop gain, which is transfer function T, basically. For instance, if you look at the top, the last equation that I have on the screen, and argue that if T as a transfer function, as a loop gain transfer function, is very large in terms of magnitude, then if T is very large in terms of magnitude at any particular frequency, then GVG over 1 plus D and Z out over 1 plus D are going to get smaller and smaller and ultimately basically 0. That means my output voltage is not sensitive against variations in the input voltage, and it is not sensitive against variations in the output current. So that's actually a good thing to have T as your loop gain to be a very large number, basically, okay? And we are going to see that that doesn't happen at any given frequency. So we have to identify, for instance, you have, I don't know, for instance, 120 hertz fluctuations in your input voltage. For instance, you have rectified power from a power outlet. There is 120 hertz, double the line frequency fluctuations in there. And in order to eliminate that in the output of your DC-DC converter, you got to make sure your loop gain at 120 hertz is very, very large. For instance, 5,000 or 10,000. So then you divide everything by 5,000 or 10,000. So basically, you're attenuating everything that appears on the as a like a audio susceptibility kind of a thing. Yes.
That means VRF is V out is VRF over H.
Exactly. So that was the second thing that I was going to write. All right. So let me, before I write that, let me just write it this way. Make sure your loop gain is very large, or you can say, what do we mean by very large? I mean at least 20 dBs. At least 10 or 20 dBs at frequencies where okay, so if you make sure this happens, then the whole, for instance, GVG divided by 1 plus T is very small, or Z out divided by 1 plus T is very small. That means you can have line and load regulation. So line regulation means your output voltage is not very sensitive or almost insensitive against variations in the input voltage. Or load regulation means your output voltage is insensitive against variations in the output current variations. So that was one basically kind of, observation. The other observation is the one that Sami just mentioned, and that is if I do not mess with the input voltage and I do not mess with the load current, okay, okay, and at the same time, so I end up the expression that I have on the very top of the screen will be simplified to V out perturb divided by Vref perturb is nothing but T over H over 1 plus T. And at the same time, let's assume our loop gain is very, very large. Okay? So if it is much larger than 1, then in the denominator, 1 is not significant. I can eliminate it, and they cancel out each other. So in the end, I have okay. So assuming that my sensor doesn't really have a transfer function, so H of S is only like a number, like division by 5 or division by 10 or something like that, that means V out is always proportional with my reference. In other words, V out is following my reference. In other words, I have a tracking system basically, so whatever I adjust Vref, then V out tends to immediately follow that Vref. So it's a good thing. So in the end, you want your V out to follow Vref basically.
Professor,
Yes.
the question is like if we design our compensator such that our loop gain is much larger than 1.
Okay.
So will that compensator work even for a discontinuous mode?
For a discontinuous
Because
mode,
that seems to be insensitive for line and load both.
it may or it may not. It depends on the converter, and it depends on the dynamic of the converter. Because if you go to the discontinuous conduction mode, the transfer functions that we got here are not valid anymore. It has its own set of equations. I cannot really say if it works or not. I mean, it depends on how much you're deviating from these transfer functions that hold for a continuous conduction mode. And then I would say, generally speaking, I would say no, it shouldn't work. I mean, it works in a sense that if your system was stable before, it might still be stable. But is it the best transfer function possible? Probably not. Good question. All right, so the observation here is my output voltage follows its reference with a proportionality of a sensing gain as long as again, assuming my reference is a DC signal with no frequency or zero frequency, my loop gain is very, very large at DC values, okay? Okay. So one, we would like to have our loop gain to be large at frequencies that, for instance, we have a significant perturbations in the input voltage or in the output load or output current. Also, we would like our loop gain to be very large at DC values or 0 frequency, because in that case we can guarantee that our output voltage is exactly tracking or following the reference. The third is not an observation, it's just a general rule of thumb, and that is we always need our system to be as fast as possible, right? So we would like to have a high bandwidth. Okay, or high feedback crossover loop, basically high. How about high loop crossover frequency? Or basically a fast transient response. Transient response. So what is this talking about? This means if we have a change in the system, for instance, all of a sudden your input voltage changes, your output voltage, your output current changes, things like that, we would like our system to recover from that disturbance as quickly as possible. So we would like to have a very high bandwidth, and I'm going to explain what that is. That means our crossover frequency should be very high. Now, before we get into the crossover definition for the crossover frequency, let me tell you the difference between a high bandwidth system and a low bandwidth system. For instance, let's say we have a converter, and in a very imaginary way, our load resistance all of a sudden changes from one number to another number. For instance, from 10 ohms to 2 ohms, or from low power to high power. Now, if you look at the transient response of your converter, for instance, you're studying your output current. Okay, now remember, the output voltage is supposed to be regulated. So when the load is high, the current is low. When the load is low, the current is high. So ideally, as soon as your load changes, you have a step change in your load resistance. Your output current also needs to have a step change. In practice, it doesn't happen. So there is a dynamic involved. So pretty much if it is, for instance, a buck converter, it's like a second order behavior involved. So you have a rise time and overshoot and things like that. Now, if your bandwidth is high, this transition happens much quicker. All right. So blue one, which responds to these changes faster, has a higher bandwidth. Okay, and this is our desire. Our desire, always we want a system to be faster, respond quickly, things like that. So how do we mathematically put it? So we are looking at this. If I draw the Bode plot of the loop gain, okay, let's say it looks like this. When my loop gain is 1 or 0 dBs, that's called the crossover frequency, because you are, for instance, going from positive dBs to negative dBs, or gains higher than 1 to gains lower than 1. So this is called crossover frequency, or omega c over 2 pi. So technically, the crossover frequency determines your bandwidth. The higher the crossover frequency is, the higher the bandwidth of your system is, and it responds to changes in a quicker way. So if I compare on the left-hand side of the screen, I had a system which had a higher bandwidth, which was in blue. For instance, the crossover frequency is, I don't know, 1 megaradians per second. The red one might be 10 times smaller, maybe 100,000 radians per second or something like that. So ideally, we would like our bandwidth to cross the 0 line or the 0 dB line at highest frequency possible to have a fastest system possible. So let me just write it down here. Oops. So, I mean, this is the technical definition of the crossover frequency. The frequency at which my loop gain crosses 1 or 0 dBs. Okay. So, high bandwidth. And another, again, this is not an observation. This is a kind of a requirement or preference. And that is overshoot and ringing. Or in a more general term, the stability of the system. We haven't even talked about the stability yet, but in the end, you want your system to be stable as well. You don't want to have a very large overshoot, and that overshoot grows over time. So this can be guaranteed by a large phase margin. Okay, so if you are curious about what phase margin is, how it is defined, phase margin is defined as the angle of the loop gain evaluated at the crossover frequency plus 180 degrees. Okay? So this is the technical definition for the phase margin. So on the Bode plots, you find the crossover frequency. Then you look at the angle graph and see what your angle is. Then add another 180 degrees to it. That's your phase margin. So in order to have a large phase margin or a stable system, your phase margin is recommended to be more than 45 degrees. If your phase margin is negative, your system is unstable, okay? But you want to be away from that with 45 degrees anyway. Okay, so let me draw this phase margin thing. I'm sure you have seen it before in a classic control class. So you look at the magnitude in order to find the crossover frequency, you have to look at the magnitude graph, and then now you look at the angle. And you see something like this, okay? So this area or this distance over here is your phase margin. Okay? If it is positive, your system is stable. If it is negative, your system is unstable. in order to be in a safe position in terms of stability, you would like it to be larger than 45 degrees, sometimes larger than 30 degrees, sometimes larger than 60 degrees. 45 is like the average number.
What if the phase margin is 90 degrees?
Your system is more stable than you want, something like that. I mean, so what I mean by overshoot and ringing or stability, this is what I mean. So again, going back to that example that we have a sudden change in the load resistance. And you are, for instance, looking at the output current. Ideally, the output current should also behave like a step change. In reality, depending on what your phase margin is, you may have a little bit of an overshoot and then settle down, or you may have a large overshoot and then gradually settle down. Okay? The blue system has a smaller phase margin compared to the red system. But they are both still stable. In the end, they all settle down to a particular number. If your phase margin is negative, then it is going to behave like this. Okay, so this is negative phase margin, or phase margin is less than 0. Okay, so that's it. So these are kind of our requirements from the system or from the loop gain. Now remember, in the loop gain, the components that appear in the loop gain is GVD, which is not something that we can really control. GM is just a constant number. This is also a constant number. So by determining what this compensation network should look like, we are indirectly basically forming our loop gain basically, and the features that it's supposed to have. For instance, it should be very high at DC values to eliminate the steady state error, or to make sure that the output voltage follows the reference, to make sure the phase margin is above 45 degrees to actually secure and ensure stability. All right. Now, before we get to this design of this compensation network, I'm going to give you some actually examples so you guys have a good understanding about a time domain simulation versus a frequency domain estimation. And I'm going to post these files on Blackboard. So here I have a very, very simple system, a closed loop system. Let's see if I can make it a little bit smaller. Display. Diagram. View. Okay. So I have a very, very simple control system. This is the output of the system, and I'm observing this output using an oscilloscope. And I'm comparing that with a reference of 1. So ideally, I want my output to go to 1. And then I have like a, I don't know, this is a loop. You can argue that this 10 is part of your loop compensation network, or it is part of your transfer function, or anyway. And for instance, this is my converter or something like that. Now, in parallel with this, I am actually looking at the Bode plot behavior of the very same system. So this is my basically loop gain, similar to what I have in MATLAB, which is some DC value of 10 times, I have a 0 at 200,000 radians per second, and the denominator is a second order system. The reason that I have chosen the second order system is because most of classic power electronic converters are actually second order systems. And omega and Q are kind of defined. Omega naught is 20,000 radians per second, and Q, the quality factor, is 1. So if I plot this thing, my loop gain, okay, let's say I'm not adding any extra component in the system, I'm pretty much happy with the gain of 10. This is the magnitude of my loop gain, basically. You can have several observations. First of all, I think I forgot to mention it last time. When you're doing a Bode plot, your x-axis, which is the frequency axis, is log scale. So here I have 10 radians per second, then 100 times that, then 100 times that, then 100 times that, okay? So you can see observations are my loop gain at low frequencies is 20 dBs, okay? It is not extremely large, but it is relatively large. This is 10 basically. 20 dBs is 10. If you are curious to see what your crossover frequency is, whenever you cross 0 dBs or 1, so this frequency is my crossover frequency, a little bit less than 100,000 radians per second. Looking at the angle or phase, this is what the phase of the system looks like. It starts at very low frequencies at 0 phase delay, then at very high frequencies it goes to negative 90 degrees of phase delay. Now, first thing that I'm curious about is this system stable or not? So remember, from the magnitude graph, I realized my crossover frequency is slightly less than 100,000 radians per second. So let's look at the phase margin. Okay, this is my frequency, omega c, crossover frequency, slightly less than 100,000 radians per second. I look at the value of my phase. It's about negative 135 degrees. I have to add another 180 degrees to it. So my phase margin is 45 degrees, which is basically the distance between my curve and the line of negative 100 degrees at the crossover frequency. Okay. So looking at the Bode plots, I can predict the behavior of the system. It is a stable system because the phase margin is positive. And in terms of tracking the reference of 1, it is going to track it, but I'm going to have a little bit of an error because my loop gain is not infinite at a DC value. It is limited to the number of 10. So if you go back to the time domain simulation and simulate it, okay, you can see the system is stable. The output voltage, or the output, whatever it is not necessarily a voltage. The output is trying to track 1, which is what our reference. There is like a second order behavior going on, but there is a steady state error in here. You can see that it is like around 0.91, something like that. Okay. So let's say you are unhappy about this and you say, I want to make my system more accurate in the sense that the steady state error between the output and the reference should be smaller. Right now, we have this much of an error. All right. So that means your loop gain should be larger at lower frequencies, right? So for instance, you can say, instead of having a gain of 10, what if I make a gain of 100? Before doing the simulation, let's look at the Bode plot and actually increase the gain. Okay, instead of 10, let's make it 100. All right. So you can see my Bode plot is going to jump up a little bit because I've increased the gain. Instead of 20 dBs, it is now 40 dBs, which is a representation for 100. My crossover frequency has shifted to the right. It was slightly less than 100,000. Now it is maybe 200,000, something like that. In terms of stability, the system is still stable because even at this crossover frequency, I have a phase margin of about maybe 45, maybe 50 degrees. So I'm expecting a system that is still stable and the steady state error is smaller. So let's look at it. Okay, now, I mean, this is a zoomed out version. If that was a zoomed in version, if I zoom out, again, you can see we are trying to follow 1, and the error is even smaller. It was before, our steady state value was about 0.91. Now it is about 0.99. So the system is more accurate. Yes?
Because the gain is like a proportional.
The gain is what?
Like a
Yeah, like a KP proportional gain. Right, exactly. You can see that still we have a little bit of an error. From here to here is our error, but the error is smaller than the previous case. So you may argue that, what if I keep increasing this gain, instead of 100, do 10,000, 10 million, things like that. And this error is going to get smaller and smaller. This particular transfer function is lucky in a sense that no matter what kind of a gain you apply, your phase margin is always going to be positive and your system is always going to be stable, which is a very special case, because in a lot of systems, once you start increasing the gain, your system is going to go unstable. So my prediction is, no matter what my gain is, my system is always stable, because if I increase the gain, this Bode plot moves up, the crossover frequency moves to the right, and no matter where it moves to, I'm always above the negative 180 degrees of basically phase delay. So my phase margin is always positive. So this is one of the good things about this system. You can increase the gain and go crazy. But this is not what in a real system you usually do, because real systems are a little bit more complicated than this. And you may start wondering, in order to eliminate this steady state error, you can never eliminate this steady state error. You can just make it a little bit smaller and smaller and smaller by increasing the gain. In order to eliminate this steady state error, you always need to have an integration block. An integration block always looks at this error and accumulatively looks at it, and if the error is 0, the integration block doesn't do anything. The output is constant. If error is positive or negative, then the integration block is never going to get tired. It's constantly reporting that my input is positive or negative, so the output is going to grow or decrease. So let me add an integration block to this system, okay, and go back to a gain of 10. Original number, oops. All right. You run the system. First thing that you observe is I have not even reached the steady state, okay? Before, it was very quick. My system was very quick in responding. Now I have added an integration block, and the system is sluggish. So I have to run it for a longer period of time, maybe 200 milliseconds. Okay, still not there, so let me do 2000 maybe. So now you can see that the output is actually tracking 1 with no error at all, because there is an integration sitting between the difference between on the difference between the output voltage and the reference, and it doesn't rest as long as they are not equal. Okay, so now you can see it is absolutely okay. It is absolutely 1. My output voltage is going to 1 exactly, absolutely 1. So if I want to go back and try to justify what I saw using these Bode plots and looking at my loop gain, so now my gain is basically 10 over S, right? Now let's see. What is that? Okay, so how about if I add it over here? 10 is there. I just add this 1 over s over here. Okay. Okay. So look at the Bode plot now. What is the crossover frequency now? 100, almost 100. I mean, let me plot it for a different scale of 0.1. You can see that my it didn't go up, but anyway, my crossover frequency is when your magnitude is crossing 0, and it is actually exactly at 10. So at 10 radians per second, you are crossing 0. So your bandwidth is only 10 radians per second. Before it was about 100,000. So this explains why the system got slow all of a sudden, because the bandwidth is much smaller now. All right, what about the loop gain in terms of, what about the phase margin in terms of stability? Okay, so my crossover is 10. Let's evaluate my phase margin at 10. It is actually about 90 degrees. It's a very stable system. As you can see, we did not even see any overshoot. It was just like a first order behavior. It was going from 0 to 1. It did not even peak at all. We didn't observe. This is like an overdamped kind of a system. All right. So now let's say you are happy with the stability of the system. You're happy that you have added an integration block in your loop to eliminate the steady state error, but the system is too slow. And in order to make the system faster, you are going to increase the gain to increase the bandwidth, basically. Okay, so let me just change this scale to 10 again. For some reason, it didn't like it that way. Okay, so let's say you're happy with everything that you did except for the sluggishness of the system. So you are trying to increase this again to increase your bandwidth. All right, so let me increase the gain one more time. So instead of 10, let me use 100. Okay, now as you can see, the crossover frequency is moving to the right. Now it's about probably, I don't know, 30 or something, somewhere between 10 and 1,000. I'm sorry, it might be maybe 100 or something like that. And in terms of stability, the system is still stable with a phase margin of 90 degrees. So let's look at the time domain simulation and see if they agree with each other. So I'm actually increasing this gain. Okay. So now you can see the system is fast. Okay, it only took less than 0.2 seconds to get to the steady state compared to the previous case, and it is still stable. All right, so that's good. All right, so you can see the system is getting faster. So since the system is faster, I'm going to reduce my simulation time to save some time. And let's say now you're getting greedy. You can say, okay, I'm just going to keep increasing the gain. The steady state error is 0, and the system is going to get faster and faster, and everything is going to be perfect. So instead of 100, let's do 10,000. You can see the system is super fast. You can see very, very fast, and you're happy with it. But now you can see it behaves more like a second order system. We have an overshoot. It's not overdamped anymore. And let's say, okay, let's go to 1 million. And now you see your system is all over the place, therefore it is unstable. So let's see if we can predict this instability at gain of, so it's like 10 to the power of 212. So let's say if we can predict this instability using our Bode plots. So instability occurred. First I changed this 100 to 10,000, everything was good. Okay. The crossover frequency has moved somewhere over here. It is moving further to the right. It's somewhere between 1,000 and 100,000. And in terms of phase margin, you're still doing good. You still have about, I would say, 70 degrees of phase margin. Now let's go to 1 million. So your bandwidth is higher. You expect your system to be even faster. So your crossover frequency is now about getting again close to 100,000 radians per second. But now around 100,000 radians per second, you can see your phase is about below negative 180 degrees. So even if you add that 180 degrees that you need to calculate phase margin, your phase margin is negative. That means your system is unstable. So we use these Bode plots instead of making a change and look at the simulation and see how it works. Graphically, can use these Bode plots to predict the behavior of your system without even running any simulations or anything. So negative phase margin because we are below 180 degrees and the system is unstable. Any questions? Okay. So what we are going to do next is, I don't think we have time for that. I was going to actually, now the knowledge that we have gained, I am going to actually apply that knowledge. Oh, by the way, there are better ways of evaluating the stability of a system rather than these Bode plots. The most comprehensive one is the Nyquist Theorem. Especially your transfer function is weird in a sense that you cross the gain of 1 several times. So the better way of doing that is using this Nyquist theorem. I'm not going to explain it, but it's again another graphical way of doing that. Let me just go back to normal gain of, for instance, 100. It is all about how many times you're circling around the point -1 in the complex domain. And if you're not circulating around -1, your system is stable. Like over here, -1 is here. My graph is actually all over here, so no problem. Let me show you a normal Nyquist. Let me just eliminate this to 1. Okay, they usually like a half circle or kind of, I don't know why it's looking like this, but anyway, it's more like a half circle or something like that. All right, I'm going to stop here. So what we're going to do next time is, so we know what we expect. So this was all about what is it that we expect from our loop gain, okay? So the next question is, now we know what we expect from our loop gain, how are we going to control or build up this G sub C, the compensation network, to satisfy our expectations? As I said, regarding the homework assignment, is if your solution is not exactly what I did at the beginning of the class, you have until Thursday before the class starts to submit your homework assignment. Yes?
Is there, could you just cover how to calculate omega z, like the right half saying 0?
Oh, how to calculate it. This system did not have an omega z.
This system, like one in the envelope, like.
How to calculate it, related to the homework assignment, you mean? How to calculate it? There is not a procedure to calculate it. This is like you develop the transfer function and some 0 appears over there. So there's no, you have to develop this. So let's go back here. So here, as you can see, I did not observe any zeros. If you see any zeros appearing here, your canonical form should be even more comprehensive, multiplied by 1 over, or 1 minus s over omega z, right? In this case, because there is no zeros, in this particular transfer function, omega z, whatever appears, you have to compare left side with the right side, and then see what omega z is. Any other questions?
Can you repeat how we replace with
Okay, so this is all I want you guys to learn. As long as a small signal model is concerned, identify the single pole double throw switch. On the left hand side, I have identified them and I've circulated with a blue circle, and then replace it with the small signal model. That's it. And then the remaining is your knowledge of circuits 1, how to find those transfer functions. All right? All right, see you guys on Thursday.